All right, so continuing on with our work on linear equations, we have two more examples to discuss. The first one is the following linear equation: dy dx plus y equals f of x. Notice this is an IVP. We have the initial condition y of 0 equals 1, and this f of x here is defined as a piecewise function. It's 1 when x is between 0 and 1 inclusive, and -1 when x is greater than 1. How do you solve a linear DE like this when your f of x function is defined piecewise, the way this is? Well, let's investigate. So first of all, this is a linear equation. It's in the same form that we want it to be in to find an integrating factor. Notice p of x is 1. That's the coefficient on my y here. So to find our integrating factor, we're going to integrate 1 dx, which is just x. Remember, don't bother with the plus c here. Okay, so we're going to multiply both sides of this then by e to the x. That's going to be e to the x dy dx plus e to the x y equals e to the x f of x. Okay, now this left-hand side we know comes down to this, d dx of e to the x y, okay, using that product rule. Now the right-hand side, this is where we have to be careful because we're working with a piecewise function. So notice I want to be able to use my initial condition here, y of 0 equals 1. The input here is 0, which tells me that I'm looking at this top line in my piecewise function. So I'm going to focus on this first. F of x will equal 1 within that interval. So that's 1 times e to the x, or just e to the x. And again, remember, that's when x is between 0 and 1. Okay? And actually, one thing that is missing here is my constant of integration. I need to be putting that plus c in there. Oh, no, I'm sorry. Not quite to that step yet. I have to integrate both sides first. That's where the plus c comes from. Jumping the gun a little bit. So if I integrate both sides, I get e to the xy equals the integral of e to the x with respect to x. So let's actually write that in there. Is just e to the x, but then I pick up my plus c here. Solving for y, I would divide both sides by e to the x, and I get y equals 1 plus c e to the negative x. Okay, and at this point, I'd like to use my initial condition to determine what c is equal to. Okay, so plugging in a 0 for x and setting y equal to 1. This is where I use my initial condition. I have 1 equals 1 plus c times e to the 0, which is just 1. So 1 equals 1 plus c, or in other words, c equals 0. Okay, putting that up here, I have y is equal to 1 plus 0, so just 1, on that interval from 0 to 1. Okay, so again, just to recap what we did, this is just like how we would solve any linear DE, but I'm working with this top line of my piecewise function to begin with, because it's within that interval that my initial condition, the x value in my initial condition would live. Okay, I work through all that work, and I end up with this solution after using my initial condition, y equals 1. And again, that's only part of the solution, because what we now have is this: y equals 1 when x is between 0 and 1 inclusive. I still need to figure out what's going on here, though. Okay, so what I'm going to do now is think, okay, ignore the initial condition for a minute. Let's find a general solution that would fit with the second line of this f of x down here. In other words, when f of x equals -1. So let's consider that next. I'm going to do this to kind of separate the work. Go like that. What if we had this dy dx plus y equals -1, right? Using the second line here. I'm looking for a general solution to this. Notice the integrating factor would be the same as before. So I'm still going to have e to the x times dy dx plus e to the xy equals -e to the x this time. this becomes d dx e to the xy, and this is still negative e to the x. This is where I can integrate both sides with respect to x, giving me e to the xy. Notice all these steps look very similar to what we just did, which is why I'm kind of blitzing through them pretty quickly, plus c there. Okay, now multiply both sides by e to the negative x, and I get y equals -1 plus c e to the negative x. Now I don't get to use an initial condition here because my initial condition here uses an x value that does not belong to the interval that we're talking about. So right now the best thing I can do is use this general solution and put that in here for my piecewise function, -1 plus c e to the negative x when x is greater than 1. Now that's not going to work as a final answer because we don't want a family of solutions. We have an IVP. We should be able to get a unique solution. So I actually do need a value of c here. And the way that we find that value of c is we use the fact that y needs to be a differentiable function, right? Even though f of x is not differentiable at 1 because there's a jump discontinuity there, our solution to this dE should be differentiable. Otherwise, we can't talk about dy dx in the first place. And as you know from Calculus 1, if a function is differentiable, then it has to be continuous as well. So what would it take for this piecewise function here to be continuous? Well, notice where this break happens is at x equals 1. Because as soon as we pass x equals 1, we go from this function down to this one. Graphically, I would want these two curves to connect. So in other words, if I were to plug 1 into this function here, I should end up with 1 as my output because this is equal to 1. That would cause these two things to match each other. I can also phrase that in terms of a right-hand limit or a left-hand limit. Your book does it that way as well. But again, what I want to do is I want to plug 1 in for x and get a 1 out here. So in other words, 1 is equal to -1 plus c e to the, remember we're plugging a 1 in there, -1. Okay, I can solve for c now. Add this over to get a 2, multiply both sides by e, and I'm going to get c equals 2e as a result. So solving this for c gives me c equals 2e. Okay, now I can take that 2e and substitute it in for the c right here. So that gives me -1 plus 2e, y equals -1 plus 2e times e to the negative x, or in other words, y equals -1 plus e to the 1 minus x is what that would simplify to. 1 minus x when, again, x is greater than 1. So let's change our answer now to y equals this piecewise function. 1 on the interval 0 to 1, and -1, I forgot my 2 down here, plus 2e to the 1 minus x when x is greater than 1. That would be our final answer for that guy. So again, the key thing here that we had to think about when solving this linear equation involving a piecewise function here is we use the initial condition to identify which of these two values we were actually going to set f of x equal to, solve as we normally would, and then we got this function. Then we investigated what would happen if we used the other value in our piecewise function. And because the IVP doesn't correspond to that, we don't get to use the initial condition there. Instead, we use the requirement of continuity to solve for c and get a final answer. Okay? All right. So we've encountered a little bit of integral defined functions in this class. And integral defined functions show up a lot when you're dealing with differential equations. The reason for that is because a lot of differential equations in the solution process involves an integral somewhere. And very frequently that integral will not give you an antiderivative in elementary functions. It's not something that you can just take the antiderivative of directly. And so for that reason, we end up with these things in our solutions somewhat frequently. There is a special integral defined function that we're going to define here. It's actually a pair of functions. We call it the error function and the complementary error function. The term error here comes from statistics. It has a very specific definition in statistics, and that statistics is one place where this function makes an appearance a lot. But it's not restricted only to statistics. It shows up in science and engineering and various different disciplines in completely different circumstances, where it has nothing to do with statistical error, but it still uses the name error function. So this is the way that we define the error function. We use this notation for it, ERF of x. We like to call that ERF. Sounds ridiculous, but that's what you'll usually hear a mathematician say, ERF of x. It's equal to 2 over the square root of pi times the integral from 0 to x of e to the negative t squared dt. The complementary error function looks almost identical. The only thing that changes are these limits of integration. Instead of going from 0 to x, it goes from x to infinity. But it's otherwise the same. Okay? Now, where is this 2 over the square root of pi coming from? That seems like a random thing to be putting there. And the reason that's making an appearance is that if we were to evaluate this integral from 0 to infinity, the integral from 0 to infinity of e to the negative t squared dt, you cannot find an antiderivative for this. But there are sneaky indirect techniques that we actually can use to evaluate this improper integral. Right? So if you were to do that, it can be shown that this is equal to the square root of pi over 2. And we're not going to derive that here. I think in Appendix A of the book, it does derive that, but you need to know about the gamma function and all this other stuff, and it's just not really worth the time. I'm going to have you take my word for it. This integral works out to the square root of pi over 2. So if I multiply both sides of this by the reciprocal of root pi over 2, I then get on the left-hand side the thing that we're defining to be our error function, but with an infinity up here, and it's equal to 1. That's important because that allows us to use this error function in statistics as what's called a probability distribution. This class doesn't deal with probability distributions, but in probability theory, if you have a function we call it a probability density function, or a PDF, if it's going to satisfy the properties necessary to be satisfied for a PDF, the integral over the entire domain of that function has to equal 1. So that's kind of the reason why this matters. But running with this, notice that if I were to take any value of x and plug it into both my ERF and my ERF-C, or my complementary error function, and then sum the two results, so error of x plus complementary error of x, that's equal to the sum of these two integrals, these two functions the way we've defined them up here. And notice, again, the only difference between those two is the limits of integration. We know from calculus that integrals have this additive property, where if you have the same integrand, then the limits of integration on the first integral go from something to some x. The limits on the second integral go from that same x to some other number, that you can combine these into the following integral. And as we just stated, that equals 1. So that's an interesting property of this. Regardless of what you plug in for x, the sum of these two functions always comes out to 1. Okay? Now, why are we talking about the error function? Well, the reason we're talking about it here is because, again, it just turns up naturally when solving some differential equations. And so we're going to do a problem where the error function makes an appearance in our solution. Notice that it's linear. It's already in the form that we want it to be in. My p of x in this case is negative 2x. So that means that I need to integrate negative 2x dx, which is equal to negative x squared. Again, don't worry about the plus c here. Okay? Negative x squared, that's what I'm raising my e to in my integrating factor to multiply both sides of this dE. So doing that, I get e to the negative x squared dy dx minus 2x e to the negative x squared y equals e to the negative x squared, like that. Okay, now I know that having multiplied by this integrating factor, this comes down to d dx of e to the negative x squared y. Okay, and then on my left-hand side, I get, well, nothing's changed yet, e to the negative x squared. Okay? What I'm going to do here is integrate both sides with respect to x, but it's going to be a little bit different than what we've seen before. I'm going to integrate these as definite integrals, not indefinite integrals. We have done this before in the previous section, and what I'm going to do is integrate this left-hand side from 1 to x. Now, because I'm using an x in my limit of integration there, my upper limit, I have to change the x's in this integrand into t's. I have to create a dummy variable. d dt e to the negative t squared of y dt. I made the mistake of not doing that in the previous section, and I don't want to make that mistake again. On this right-hand side, I'm doing the same thing. Integral from 1 to x, e to the negative t squared dt. Change the x into a t. All right, now I'm going to leave this guy alone on the right-hand side because I know that I can't evaluate that directly. Instead, I'm going to try and put it in terms of the error function, but I'm just going to wait a minute before doing that. On this left-hand side, from the first part of the fundamental theorem of calculus, I know that this is equal to my integrand after plugging an x in. So in other words, this still serves the purpose of canceling out that d dt, and this becomes e to the negative x squared y. And that equals this right-hand side. Okay, now I can isolate my y. Y is equal to e to the x squared. Multiply both sides by e to the x squared. One thing I should have done actually all the way up here, I should have included my plus c. Even though I'm not able to evaluate that integral directly, I do know that a constant of integration is going to come out, and it needs to be there so that I have a parameter to work with. 1 to x, e to the negative t squared dt. Okay, now if you notice, this integral, it looks similar to our error function that we defined here, but it doesn't have the correct lower limit of integration. First of all, it's worth noting, why did we start with a lower limit of 1 in the first place? Why didn't we make it 0? And remember, when we did this before, we're using the x value in my initial condition, okay? Because that allows us to plug some stuff in. I forgot my plus c again down there. Let's use our initial condition here. If I plug a 1 in for x and set the y equal to 1, what does that do? Well, plugging a 1 in for y, that's equal to e to the power of 1, because I'm plugging a 1 in for x as well, times the integral from 1 to 1 of e to the negative t squared dt, plus, and I realize I actually forgot to write e to the x squared here, c times e to the first power, which would just be e, so that. Okay, now if you have the matching lower limit of integration and upper limit of integration, it doesn't matter what this integrand is, that always comes out to 0. That's the reason why we wanted this lower limit to be a 1, because once we use our initial condition, this entire term here goes to 0. So this is where we use our initial condition. Okay, that gives me 1 equals CE, or in other words, C equals e to the negative 1 after solving for C. Okay, so that allows me to go back to my general solution up here, plug in e to the negative 1 for C. So that gives me this, y equals e to the x squared times the integral from 1 to x of e to the negative t squared dt, plus e to the negative 1 times e to the x squared. Let's simplify that a little bit. E to the x squared, integral from 1 to x, e to the negative t squared dt, e to the x squared, or sorry, plus e to the x squared minus 1. Okay, now I can technically just stop here if I wanted to, but nowhere am I making any mention of the error function. So I actually want to do that next. What I can do is manipulate this integral right here. I'm going to do that off to the side. So if I were to write 1 over x, the integral from 1 over x e to the negative t squared dt. One thing I could do is write this as the following. I could say that this is equal to root pi over 2 times 2 over root pi integral from 1 to x e to the negative t squared dt. Right? So I basically just multiplied something by its reciprocal out here so that it goes to 1. And the purpose of doing that is in my error function, I need to have that factor of 2 over root pi showing up. Okay? But I also have an issue. If I want this to look like my error function, I need a 0 down here, not a 1. So what would that, how can I change that? Well, notice I can write that this way. Root pi over 2 times 2 over root pi times the integral from 0 to x e to the negative t squared dt minus 2 over root pi times the integral from 0 to 1 e to the negative t squared dt. Okay? I'm playing with the limits of integration here to break this integral into a sum of two integrals, really a difference of two integrals. But we know this property from Calculus 1 that you can do this. You can split this integral up this way. And the reason for doing that is in both of these integrals, my lower limit of integration is now a 0. I also have that scalar, that constant factor out here that I need in order to rewrite these in terms of the error function. So that means that this thing is equal to root pi over 2 times this whole thing is erf of x, error function evaluated at x. This guy right here is erf of 1, because you notice it's the same as this, but I've plugged a 1 in where the x is. So this expression, putting this thing in terms of these erfs, these error functions, I can rewrite the integral that showed up in my solution this way. So that means I have this, y equals e to the x times, actually let's take this constant root pi over 2 and bring it out here. Root pi, let me try this again. Y equals root pi over 2 e to the x squared times erf of x minus erf of 1. I just like saying erf, plus e to the x squared minus 1. Okay, and that would be my solution. Oh, I realized that was off the screen. Sorry about that. So you might be looking at this and thinking, why would I do that? I mean, this doesn't really look simpler than what we already had up here. So what's the purpose of just putting this in terms of erf? And the reason for that is because the error function shows up so often, we have tabulated values of this thing. Tabulated means we've calculated the error function at a whole bunch of different inputs and put them into tables. Now, if you come up here, if this is the solution to my original DE, and I am trying to plug something into this to get a specific point, say if I try to plug in 2 for x, I don't have a very good way of evaluating this integral right here, the integral from 1 to 2, and I would need to do that in evaluating this function at 2. However, if I plug 2 into this guy down here, remember that erf of x, we have tabulated values for that. So we could use a table to find the correct value for this instead of trying to deal with this integral directly. That's the reason why we kind of prefer to have it in this form. All right, that's it for linear equations.